As our next topic, we are going to cover incremental analysis. As I'd mentioned earlier, incremental analysis is just one way of viewing a really cool trick that you will be learning about in this sequence of videos. That trick is called the small signal trick. You can think of this trick as a way of taking circuits that might be nonlinear and using this trick, use those circuits in a way that makes their behavior more or less linear. Now, an incremental analysis can be thought of as a way of analyzing such circuits. So before we begin talking about exactly what the small signal trick is, I just would like to put things into some perspective. So you are in the 6002 world, and in this world we made some simplifications called the lumped circuit simplifications and developed the lumped circuit abstraction. And as soon as we made this abstraction, we got into this EECS playground of ours, and we talked about several techniques for learning about for analyzing circuits, like the KVL, KCL method, the node method, the composition rules, and so on. Following that, we said if circuits were linear, so for example, if I have a circuit containing only resistors, that is linear. We also talked about various rules that make circuits linear. Those circuits have to follow the principle of homogeneity, the principle of superposition, and so on. So when I have a linear circuit, then I could use techniques like superposition and Thevenin and the Norton method to analyze those circuits. Then there was the other class of circuits, nonlinear circuits, and we looked at techniques like the analytical method and the graphical method to analyze those circuits as well. And fundamentally, analytical and graphical methods were simply an application of the basic node method that we learned about earlier. Within the nonlinear domain, we also looked at the domain of digital circuits. Now, digital circuits are inherently nonlinear. Now, we have a switch as an example here. This is a switch. It's implemented using a MOSFET, and these are nonlinear devices. When I have circuits like this, one of the things that is interesting is that for fixed input values, so in this case, I have an input A and an input B. If I fix the values of A and B, then something very interesting happens. Digital circuits begin to look like linear circuits. So, for example, out here, for a fixed value of A is equal to 1 and B is equal to 1, I get a fixed switch setting for all my resistors. And what I end up with is a network of the sort, and this can be analyzed using linear techniques. This is quite nice. And then we said within the nonlinear domain, I have promised you that I'll cover something called the small signal model. Okay, I haven't told you what it is. So when I look at the nonlinear domain, and if I look at a particular use of these nonlinear circuits, a particular stylized, disciplined use of circuits that I will talk about today, then what is amazing is that those kinds of circuits also can be analyzed using our linear techniques. Okay, so let me start with a review of the kinds of things that we will cover in today's sequence, and also very quickly look at what we've done so far. So in the nonlinear arena, we have looked at analytical methods, graphical methods, and we briefly looked at the piecewise linear method to analyze circuits. And today, as I said, we will cover the small signal method or the incremental method. And you can read up a lot more about this in section 4.5 of the textbook.